Hey everyone, welcome to today's video. Today we'll be going over a basic introduction to calculus. So the two major concepts we'll be talking about today are differentiation and integration. And so let's dive right into it. So when you're talking about differentiation, when you differentiate a function, you're looking at how the function changes in an infinitesimally small change in the input quantity. So like let's say for instance, we have a car traveling at 6 meters per second, right? So let's say we have a car, all right, nice art skills, going at 6 meters per second. And let's say we have a position function s of t. So this position s as a function of time. At a given time, we can find the car's position. Let's say its position is given by 6 times t. Basically, at time like t equals 2, it's going to be at 6 times 2 meters to the right. So that's the position function. At a given time t, we can plug it into this function to find where the car is located. All right, pretty cool, pretty cool. Now, let's say we differentiate this function with respect to t. So when we're differentiating with respect to t, that means we find how s changes as we change t by an infinitesimally small quantity. So let's say we increase time by a very, very small quantity. That quantity is called dt. So we're going to get 6 times t plus dt, right? And we can expand this and treat dt just like any other variable. So we get 6t plus 6 dt. And now if we look at how much our position has changed, that's s of t plus dt minus s of t, right? So this is at the new time, this is at the old time. And the car's position has changed by, originally it was at 6t, now it's at 6t plus 6 dt. So the total change in position is 6 dt, okay? And we call this infinitesimal change in s ds. All right, so we have ds equals 6 dt. What this is saying is, if you take a time segment of like 1 femtosecond, okay? So that's like a very, very small amount of time. Within this 1 femtosecond, the car is constantly traveling at 6 meters per second. That's what it's saying. The speed of the car with respect to time is 6 meters per second. So a more accurate way to write this is actually ds dt. So the change in position over change in time, also known as speed or velocity for those of you who take physics, that is equal to 6, meaning that at any given point of time, this car is traveling at 6 meters per second. So we can write this expression. That's exactly like a distance equals rate times time formula just rearranged. So it's exactly like what we've already seen. I would like to say there's another way to notate this, which is s prime of t. All right, it means the exact same thing, it's just different symbols. All right, another way to interpret the derivative is on the graph. So let's say we have a graph of position versus time again. This one is not as nice, so s of t equals 6 times t, which is what we had originally over here. That was a pretty nice and easy function, but what if our position function is like this super weird and wavy looking thing? Well, at that point, the derivative still represents how fast the particle is moving at a specific point in time. So let's say we pick like time t equals 5, right? So I'm curious, after 5 seconds, how fast is this car moving? Well, all you have to do is draw the tangent line. The tangent line is the line that intersects this graph at exactly this point. Okay, it's a little hard. Maybe let me pick a different spot. Let's say like t equals 3. All right, a little bit more over here. At time t equals 3 seconds, you can do this for any time. It's just that I'm picking time t equals 3 because drawing the tangent is a little bit easier. That's the tangent line, because it only intersects the graph at that one point, at time t equals 3. So in your x coordinate would be 3, your y coordinate would be s of 3. Okay, whatever that is, we don't really care. So when we look at this, the slope of the tangent line, actually let me stick to orange. The slope of tangent line is actually equal to ds dt. So the change in position over the change in time, whatever that is. In this case, since our graph is wiggly, that ds dt, that slope of the tangent line, changes. So if I pick this point, the slope of the tangent line would be a little more steep. If I picked this point, the slope of the tangent line if I picked this point, the slope of the tangent line would be steep and negative. If I pick this point, it would be steep and positive. So it just depends on wherever you are. You just find the tangent line and find the slope, and that's the derivative. Now let's talk about integration, which is the other major concept in calculus. So integration is just the exact opposite of derivatives. In derivatives, you're looking at how a quantity changes with respect to a very small change in the input. In our case, the input was time. In integration, we're talking about adding up these infinitely small changes over larger periods of time. Okay, so let's say for instance, we go back to our speed, ds dt. This is how fast our position changes in a very small quantity of time. If we integrate that from t equals 1 to t equals 3 with respect to dt, alright, this might look pretty intimidating, but let me explain. So, what we're doing by taking this derivative and integrating it is that we're saying we want to add up these little tiny differences over this time interval from t equals 1 to t equals 3. So between this time interval, each moment in time, we see ds dt equal to 6. So this particle, or this car, is moving to the right at 6 meters per second. And at this point too, at this point too. We want to see if we add up that movement over this time interval, how far has the car gone? And that's all this integral sign, this symbol, this notation is saying. All right. Now I do want to point out one thing here. You can treat this dt just like another variable. So you can actually just calculate cancel out dt in the numerator and the denominator, and you end up with t equals 1 to t equals 3 integral of ds. These mean the same thing for the most part. The technicality or the technical difference really only comes in when you're taking like a hard math course, a pure math course like calculus or something. But at least in physics and chemistry, this difference is small. We don't really care about the notational differences. Okay. Anyways, so we've added this difference up from t equals 1 to t equals 3. All right. And there's another way to notate this. It's delta s. So earlier we used ds for a very small change in the position function over a very small change in time, right? Now we're using delta s. Delta is like the same idea, but over a longer period of time that we can actually measure. It's not infinitely small. It's like from time t equals 1 to t equals 3. We can actually calculate how far the car went over this interval. It's not just some abstract, infinitely small concept, okay? It's like an actual difference. In fact, we can do this for any initial time and final time. So we could start with any t initial, integrate to any t final, and this expression would give us delta s from t initial to t final. Basically, how far the car went, how much the car changed its position between the initial time and the final time. Alright, let me also point out that sometimes integration is seen as finding the area under the curve. So what exactly does that mean? Well, let's say we have a curve, but this time our curve is ds dt, okay? Also known as s prime of t. So this is the velocity in the physics sense. This is the speed of the car. Integrating, so this is our t equals 1, right? Our initial time, and this is t equals 3, our final time. Going from t equals 1 to this infinitely small point in time afterwards, let's say 1 plus dt, we see that the total distance traveled by the car was the sum of all of these velocities throughout this infinitely small period of time. So this entire rectangle is the distance that this car managed to travel. And if you don't believe me, you can look at the units. The width of the rectangle is time, well, let's say seconds, right? And the height of the rectangle is measured in meters per second because that's velocity. And if you multiply meters per second by seconds, you'll get meters again, which is why the area of this rectangle looking thing is actually the total meters, the distance traveled by the car in that interval of time. And you could do that again. You could look at the next infinitely small period in time and the next infinitely small period of time. And if you keep on doing that for all these infinitely small periods of time, over time, you just end up shading in this entire area underneath the curve between time t equals 1 second and time t equals 3 seconds. So from this time to that time, how far did it travel? To answer that question, all you have to do is find the area under this curve. And how do you find the area under the curve? Using this handy dandy integral right here. And I think that's where we'll stop for today. I hope you guys enjoyed this basic introduction to what differentiation and integration means in calculus. There are specific rules and formulas for if your position function looks like this, right? Like a specific exponent of t, then you can calculate the integral using this formula. You can calculate the derivative using this formula, and blah, blah, blah. There are a bunch of different formulas. For that and more specifics and details, check out the handout I've linked in the description. And yeah, I hope you guys enjoyed this video and found it helpful. Stay tuned for more.